Welcome back. Uh, so, now we have f, we will assume that continuous and has moderate decay. Of course, then this is integrable as we have seen earlier, and then now we have characters. Therefore, we can now define Fourier transform. So, now the characters are e to the power 2 pi I j x for j belongs to, or this is a function on R. Therefore, I will write j dot j belongs to R. So, we have analogously defined f hat of xi for j belongs to R, integral minus infinity to infinity f of x e to the power minus 2 pi I j x dx. Now, easily one can see that mod of f hat of xi, if I am using the triangle inequality under the integral, then this would be lesser equal to minus infinity to infinity mod of f of x dx. Now, this we know that is a finite number lesser equal to some constant a, which is less than infinity. Therefore, first observation for us that f hat is bounded. That is our first observation. Now, the first thing what we had proved there is something called a Riemann-Lebesgue lemma. So, now here do we have the analog of Riemann-Lebesgue lemma? As a matter of fact, we have. So, now this is the theorem, what we call the Riemann if f is like continuous and moderate decay, then f hat is also continuous, and second is that f hat of xi, this goes to 0 as mod xi goes to infinity. Just like in the case of the Fourier series, if we have a Riemann integrable 2 pi periodic Riemann integrable function, then the Fourier coefficient will go to 0 as mod n goes to infinity. So, the proof will ideally follow the same idea what we have employed there. So, this is integral minus infinity to infinity f of x minus 1 by 2 j e to the power minus 2 pi I j x. This for j not equal to 0. So, because we are interested in j mod j goes to infinity. So, we are not bothered about xi is equal to 0. So, for large j we are interested. So, we can talk about 1 over 2 j. Now, if I make a change of variable what we have seen earlier, this is f of x and then e to the power minus 2 pi I j, then this one becomes x plus 1 by 2 j dx. This is equal to minus infinity to infinity f of x e to the power minus 2 pi I j x into e to the power minus pi I dx, 1 by 2 j will get cancelled, e to the power minus pi I is negative 1. So, this is minus f of x, which is equal to minus of f hat of xi. So, therefore, twice f hat of xi, this is equal to integral minus infinity to infinity f of x e to the power minus 2 pi I xi x dx, and minus f hat of xi is minus of this. Therefore, this is minus infinity to infinity f of x minus 1 by 2 xi e to the power minus 2 pi I xi x dx. Now, this is equal to minus infinity to infinity f of x minus f of x minus 1 by 2 xi e to the power minus 2 pi I xi x dx. Now, again, so this minus infinity to infinity is we can take for minus n to n, and f is a continuous function, therefore, uniformly continuous on a finite interval. Then, and if mod xi goes to infinity, then this becomes 1 by 2 to the 1 by 2 xi, this goes to 0 as mod xi goes to infinity. So, therefore, we can appeal to the continuity part of f such that in the finite interval this is less than epsilon like our earlier argument, and so this we can say that this converges to 0 as mod xi goes to infinity, because tail part will always be less, and then on minus n to n we will appeal to the continuity of f, and our 1 over 2 xi is very small because xi is large. So, we get the smallness overall. So, this what we have got is the Fourier transform, the Riemann-Lebesgue lemma. So, what it says is that it is bounded. So, now is it I mean one can ask that if f has a moderate decay, is f hat going to have moderate decay? Because finally, I mean what we want, that if we would be chasing for inversion formula or Parseval identity. Now, to get the inversion formula, then we have to write integral minus infinity to infinity f hat of xi and something. Now, that must be integrable. A priori, we have no idea that whether this f hat is going to be integrable or not. What we have seen is that only f hat is bounded. Now, let us see that we are giving a moderate decay, then f hat may not have a moderate decay. However, if we put the condition that if f is C1, that means if that means we take f and f prime both continuous and moderate decay. Suppose we are imposing the condition on the f prime, which also has moderate decay, that is integrable in our sense. So, then let us look at f hat of xi. F hat of xi, this is going to be equal to let us say limit n goes to infinity minus n to n f of x e to the power minus 2 pi I j x dx. This now this part is this is the integral. So, I will take, suppose xi is not equal to 0, then this is f of x into e to the power minus 2 pi I j x by minus 2 pi I j, this is minus n to n, then minus plus 1 by 2 pi I j integral minus n to n f prime of x e to the power minus 2 pi I j x by parts. Now, as you can see that f has a moderate decay, therefore, for large n when we are taking, therefore, f this is goes to f towards the infinity has to go to 0, because mod of f of x is lesser equal to some constant by 1 plus x square. So, then the first part will go to 0, and the second part f prime we are assuming that it is integrable. So, this we can write it as 1 by 2 pi I j minus infinity to infinity f prime of x e to the power minus 2 pi I j x dx. Now, if we push the mod here, so what we get that f hat of xi is less or equal to some constant by mod xi, and this the constant of course is the integral over mod of f prime. So, this is no more dependent on xi. So, now if we give certain smoothness on our function f, then we see that we are getting some decay. So, just with once differentiable and f prime has is integrable, then what we are going to get that f hat has a decay like 1 over mod xi, but we if we want to get mod xi square kind of the decay, then if we do take f to be twice differentiable and double derivative as also integrable in our sense, then by doing time and again this another integration by parts to this is going to give us, we will get a factor of 1 by 2 pi again. So, if let us note it down, f belongs to C 2 with moderate decay on f prime f double prime, then what we can see is that mod of f hat of xi is less or equal to some constants by mod of xi square away from the origin. So, we are giving a differentiability on f, we are capturing some decay on f hat. So, this constant will be the modulus of f double prime of x integral and 1 over 4 pi square. Okay. So, in general, if f is in C n and n times differentiable and all those f k moderate decay, k is equal to 0 to n, then what we get mod of f hat of xi is lesser equal to some constant times mod xi to the power n for large n. Okay, so that is what we have seen. So, now let us to do some Fourier analysis. Let us try to compute some Fourier transform of integrable function. As you can see that we have assumed continuity for our purpose to prove certain things and all, but to define the Fourier transform, what essentially what we need is that the mod f is integrable minus infinity to infinity mod of f of x. So, remark to define Fourier transform, we need is finite. That is all what we need. Then we can define f hat of xi is integral minus infinity to infinity e to the power minus 2 pi I j x dx. So, in this context, so let us do some example. Let f of x, this is equal to indicator function of minus 1 to 1 x. So, therefore, this is integrable function and f hat of xi then would be equal to minus 1 to 1 e to the power minus 2 pi I j x dx. So, this is equal to, if xi is equal to 0, then what we are going to get, this is equal to 2. And if xi is not equal to 0, then this is e to the power minus 2 pi I j x by minus 2 pi I j from minus 1 to 1. Obviously, we know what this quantity is. So, this is going to be, I can erase this now and I can write this, this is sine 2 pi xi by pi j. Okay, if xi is not equal to 0. So, that is one. Then the second thing, let us try to do it for a continuous function. Let f of x, this is equal to 1 minus mod x if mod x is lesser equal to 1, 0 otherwise. So, this is a continuous function, because this function will look like at 1 minus 1 and 0 here, 0 here. So, this is a continuous function. So, now if we would compute the f hat of xi, so this is the function is now supported on minus 1 to 1. So, rest of the integral is going to vanish. So, now this is what we need to compute. Okay. So, minus 1 to 0, then 1 plus x e to the power minus 2 pi I j x plus 0 to 1, 1 minus of x e to the power minus 2 pi I j x dx. So, this if we are going to combine these two. So, this is going to be nothing but 0 to 1. So, if you just compute this to integral, as you can see that x e to the power minus 2 pi I j x, if we make a change of variable, then this is going to get 0 to 1 minus of x e to the power 2 pi I j x dx, and this is plus 0 to 1 minus of x e to the power minus 2 pi I j x dx. So, if you do, then what you are going to get is that the integral 0 to 1 twice 0 to 1 minus of x cos 2 pi j x dx. Now, you apply integration by parts. So, once you apply the integration by parts, then by computing, if we complete the computation, then what you are going to get that f hat of xi, this is equal to sin pi xi by pi xi whole square if xi not equal to 0. That is a very easy computation, as you can see that the first one would be twice cos 2 pi xi x by x evaluated at 0 and 1, and integral is sine. So, that is going to vanish, then 1 minus of x, that is going to vanish, and then in the other part, if we are doing this, then derivative of this is sin 2 pi j x by 2 pi j, and the derivative is minus of 1. So, which you are going to get in the terms of the cos, and then 1 minus. So, this will actually give you the 1 minus cos 2 pi j, that is 1 minus cos 2 theta, that is 2 sin square theta. So, just by completing this argument, you will see that f hat of xi is equal to sin pi xi by pi xi whole square, sin square pi xi by pi square xi square. So, now, so essentially what we observed with the similar I mean the computation and the earlier observation. So, if we are taking a function having some good decay and they are differentiable, then the Fourier transform, because of the differentiability we are producing certain decay, and then the Fourier transform will is well behaved. So, to see that class of function, so before introducing that class of function, let me give you one example which is very important. Now, what you define f of x, this is equal to e to the power minus 1 by x minus, or rather minus 1 by x into x minus 1 if x is in 0 and 1 and 0 otherwise. That what we see is that this is 0 here, and so we know that e to the power minus 1 over x square, that is differentiable at 0, and so hence what we get some function like something like this. So, this is a function f is infinitely many times differentiable, and has compact support So, this class what generally it is denoted by C infinity of r. So, this of course has moderate decay and so on and so forth, and it is infinitely differentiable. Therefore, the f hat, the Fourier transform, is going to have good decay. So, at least it has the, polynomial decay, in the sense that if you hit the function with a polynomial, then again that is going to be under our control. So, now in the next lecture, what we will be doing is to find an appropriate space in which we will have a very nice Fourier analysis result. That is in the next lecture. Thank you.